Second is if we are having here this tangent vector and we have the point. So as we have discussed in our parametric equation of the lines, we can say that we can find the equation of the line passing through the point P and parallel to vector t. Then we can find tangent line. So this line will be tangent line because this is parallel to tangent vector. Tangent line to the curve C at point P is defined. You can find tangent line here at point P passing through the point P parallel to vector r dash of t. So this is, we can have the in this case we can define the equation of the line. I will give you the example to explain this one further to you. So here you can just take this definition. Now you can have here note 5 that give us the concept of the unit tangent vector. So we have defined also the tangent vector. We can find unit tangent. We have the tangent vector. We can easily find the unit tangent vector. This is not a new concept because we have already seen where vector A. Want to find unit tangent vector, and just divide by the magnitude of the vector, we get unit tangent vector. Because now we have the vector r dash. So we want to define the unit tangent vector, we just divide by the magnitude of r dash, that will become unit tangent vector. So denoted by t of t, and this give me r dash of t, and just divide by the magnitude of r dash of t. That's my unit tangent vector. So I will give you the example to explain this idea which I have just mentioned above. Definition is higher order derivative. We have already defined first order derivative. Higher order, if the function are differentiable, then we can find the higher order derivative of this one. We are having here for r of t is equal to f of t I plus g of t j plus h of t k. So we can define here this is dr by dt. So dr by dt is our first order derivative is equal to df by dt I plus dg by dt j plus dh by dt k. You can find the derivative of this parametric functions f of t, g of t, higher, they are defined higher derivative. We can find the higher derivative of d2r by dt square. Second order derivative d2r by dt square is equal to d2 f by dt square I plus d2 g by dt square j plus d2 h by dt square k. We can extend this one also. We can have the second derivative, third derivative. There is no problem with that one. I just give you the geometrical interpretation of this one as a note, how we define geometrically this derivative. So for example, this I am having here my z-axis. This is my y-axis. That's my x-axis, x-axis, y-axis, and z-axis. I have this curve, and there is a point P on the curve, and I have here the vector value function defined by r of t. So this is my vector value function defined r of t. Now if I take here the derivative of this one, then this derivative is r dash of t, is tangent to the curve. When I take the second derivative, this is my second derivative, r double dash of t inside the curve. So that's the idea. We can just have the values and we can just sketch them, and we can see that how these are behaving, this r dash of t and r double dash of t. So this is the r double first derivative, second derivative also. We will discuss further about this one, and I give you some example. We use the application of this, and then we can go further. We apply our definition of the derivative by using this example. We given the vectorial function r of t is equal to t I plus t square j plus t cube k. Domain of t, r of t is bigger than 0, t bigger than or equal to 0. Want to find the first derivative, second derivative, dot product, and cross product. So the A, want to find the first derivative. We are given r of t is equal to ti plus t square j plus t cube k. So we get r dash of t, derivative of t is 1, therefore t g of t is 2t square, we get 2tj. H of t is t cube, we get 3 t square k. So this is my first derivative. This is why I can find here b is my second derivative. R double dash of t is equal to derivative of 1 is 0. So it will be 0. We get here 2j plus 6tk. So these are my derivative of the functions. I have the derivative of the vector value function, first derivative, second derivative. C, we want to find the dot product. R dash of t dot R double dash of t. Just to remember that one, when we having here two vectors a and b with the component a1 I plus a2j plus a3k and b1i, b2j, b3k. The dot product is a1 b1 plus a2 b2 plus a3 b3. So that's our definition of the dot product. We apply this definition and we find here the derivative, the dot product R dash of t dot R double dash of t is equal to a1 b1 is 0, a2 b2 is 4t, a3 bt is 18 t cube. So I can write here my result is equal to 4t plus 18 t cube. So we can also find the cross products R dash of t cross R double dash of t. We use the definition of the cross product. I am here I, j and k. The component of R dash R, we are having here this is equal to 1, 2t, 3t square, and component of R double dash is 0, 2 and 6t. So I just solve this one. Opening this determinant, I'll get here this equal to 12t square minus 6t square I. Then we take j, this is not plus j, is minus j, and here minus sign, minus j, the component of j are 6t minus 0, 6t minus 0 j, and component of k is 2 minus 0, 2 minus 0 k. So I rewrite this one, I get here 6t square I minus 6t j plus 2 k. So that's my result. So this is a vector, again vector value function, the cross product of two vectors, whereas when you have dot product, this was scalar, this function, and we having R dash and R double dash. We continue this one and we take next example. In next example, we try to find the equation of the tangent to the curve. We having here, I want to find the equation of tangent line because as I told you, and note that we having here the point and we are having the vector at that point, and we can find the line passing through the point and then parallel to that vector. So that will be our tangent line.